So, welcome to this new lecture, and today in this lecture, we'll start with this idea of relational structure. Uh, we studied algebraic structure in quite detail. We saw different kind of algebraic structure. Now, in this lecture, we will start with relational structure, and I think in lecture 10 or maybe lecture 11 we talked about what relational structure is. We saw, I gave some examples, but it was mostly philosophical. Now in this today lecture, we will do it formally, and I will show one particular example of relational structure, or maybe two, and then from there we'll see where does it goes. Okay. So first of all, about relational structure is that it is relational structure is quite fundamental, I would say, than algebraic structure. And the reason for this is algebraic structure is about operation, right? We know it. It's about operation. For example, arithmetic. Arithmetic is itself an algebraic structure, and it's a field which is an algebraic structure, and all algebraic structure is about operation, and operation is about a kind of function. But how do you build function? The function is built by using relation. Without relation, there is no idea of function, you see. And that is why I say relation is more fundamental than algebra. And mathematics is about relations, right? It's about relation. And the example of relational structure is today I'm gonna give is from set theory. It's from set theory. And the first example of relational relation is belongs to. You see, the idea of belongs to. And belongs to is relation. It is not an operation. It's an relation. Now, it is a binary relation, not a binary operation. Why it is a binary relation, that we will see in a few minutes. But yes, the concept is that we will begin with belongs to, and then we will go into geometry again. That's our home. And so let's see, maybe we should start doing it, you see. So what is a relational structure, right? And to understand relational structure, we need to understand few things, which is set. Then we will begin with ordered pair, the concept of ordered pairs, and then Cartesian product, then relations, then functions. Not functions, only up to relations, because we are not going to deal with algebra right now. All right. So maybe I could do it on the paper now. So the concept is it's called relational structure. This is what we are gonna do today. Now we will begin with set Then we will begin. Then we will talk about idea of ordered pairs, and then we will move to Cartesian product, and then relation, right? And from there we will study the usual, our objective of this lecture, relational structure, right? So let's begin with set. Everybody knows the first is set. What is a set, right? We know it. A set is just collection of some object that could be, let's say, A, B, C, D. It could be finite, it could be infinite. We don't have to worry about that. So it's an example of set. Now, a set has some operation, right? We can define some operation. But before doing that, before going into operation, let me say one very important thing, right? Set theory. After saying this, we will talk about operation. Let me circle it here so that I do not forget. So set theory is this: V comma belongs to. This is itself an relational structure. This is itself an relational structure. Why I call this set theory? Well, what is V? V is, you have to be very careful, V is not one particular set. That is what you have to remember. I am not talking about this set or set of real number or set of natural number. No, this V is not one particular set. V is the whole universe. You see? This V is whole universe, and here lives all kind of set, S1, S2, S3, Sn. Every set that we can think of is in this set V. Now, is this a set? Is V a set? Because V contains all the set that we can think of. Everything, every set that we can come up with is in the set V. But is that a set? Well, set theory does not allow that. Set theory does not allow the such a set where it contains all set that could exist. And the reason is simple. Can you think why? Why cannot there exist such a set that contains every kind of set? Well, the answer comes from power set, the notion of power set. And we will talk about this, and then this thing will be clear, and I will answer it later. Why it is not allowed. For now, so this V comma, this is a symbol of belongs to. We say it is belongs to. So this is itself an structure, not algebraic structure. It is relational structure. Now, set theory is this. This is set theory. And then belongs to has to satisfy axioms. And we know the axioms of set theory, the usual axioms, right? So this relational structure with some axioms, we called ZFC axioms, it becomes set theory. But this is language, it's a meta language. This V comma belongs to, it falls within meta language category. we cannot talk about this object within inside set theory. This is very important. We cannot talk about this structure inside set theory because this is not a set, so we cannot talk about it. Simple as that. Why it is not set? It has to do with power set. We will make it clear later. But this structure cannot be talked inside set theory. It is the theory of set. It is the meta language we use to develop set theory itself, the language itself. Think very carefully. It's like, what I'm trying to say, this is meta language that we are using to create a language called set theory. If you are using this to create set theory, you cannot talk about this inside set theory, because inside set theory we do not have meta concept, right? This is a meta concept. This cannot be talked inside this. Well, for example, what I'm trying to say, that a system, let's say a system X, cannot talk about itself. It's a paradox. It's a self-referential paradox. It cannot talk about itself, a formal system. And mathematics is formal. It's a formal system. Formal system means it has some axiom, it has to follow that. It cannot escape it. It has rules. It is a rule-based game, right? And those rules cannot talk about its own rules, right? And a computer cannot talk about its own rules. It cannot break it. It cannot escape the rule. See? A computer cannot escape the rule. And artificial intelligence cannot escape its program, right? Similarly, set theory is like a machine. It's a machine. It cannot escape its language and go and talk about this structure. It is impossible, because this is what creates set theory. But we cannot talk about this inside set theory. Alright? Now why it is not a legitimate set, we will talk about this later when we will develop concept of power set. For now, let's talk about set. So we have set. This is the first thing. Remember, our goal of this lecture is to talk about relational structure. Okay, so we are building the theory. So set. So we have set. Let's say we have set A, B, C, D. Right? Now we have a symbol belongs to. Right? We have a symbol belongs to. It's an operation. It's an relation. How it is defined? Well, it is defined as A let's not define it this way. The moment I define this way, I will leap to concept of Cartesian product. So let's throw it away. How belongs to is defined that it is going to take an element from this set, this, right? For example, let's say X, and it's going to check is X belongs to A. That is what it is gonna do, right? So belongs to takes two things, an element of the set and the set itself, right? So it's a binary relation, an element and a set, right? For example, A belongs to A. Is it true or false? Well, A belongs to A. It is true. So this belongs to has two input. This one, first one is element. First is always element, remember this, it cannot be set. And the second one is set. So belongs to is a binary relation. It's going to take two things, x and x. X is element and x is set, and it's going to check if x belongs to x, right? So we only need these two things to have whole set theory. Now we define some operation between two set. Let's say we have given two set A and B. This is symbol of AND. So we have given two set A and B. Now we have the concept of union. We have concept of union. And what union does, the notation is U. So A and B, and it is going to produce a set which has some element x, such that, what is the nature of x? Well, this x must belongs to A, right? Must belongs to A, and x also must belongs to B. So union is defined only using a symbol belongs to, because in set theory we have only one symbol belongs to, and from belongs to we are going to create different kind of relations, right? So this operation, x belongs to A and x belongs to B, if this holds, we get A union B. Example could be A equal to 1, 2, 3 A, and B is a set x, y, z 2, right? So what is the union of these two sets? Union means, using these definitions, it is going to contain x, some elements here, that will be x, and those elements must belongs to A and B both, right? Oh, I am sorry for this. This is not AND. It should not be AND. It should be OR. Okay? It should be OR, not AND. So it should either belong to this or either belongs to this. So this is union. So one belongs to this, it does not belongs to this. That's fine, because it says either belongs to this or either belongs to that, and we're gonna put it in our set. So are we gonna put one here? Yes, of course we can, because it belongs to A. It doesn't matter it belongs to B or not. What about 2? Well, 2 belongs to this, 2 belongs to this. It does not matter. It can belongs to this, right? It says OR, so we can 2 also. Similarly, 3 only belongs to A, does not belongs to B, does not matter. It should belongs to any one of them. A also. Similarly, X, Y, Z. So this is how we evaluate A union B. Okay. Now there is one concept which is order of a set. Remember, a set A equal to 1, 2, 3, a set A equal to 2, 1, 3, or a set 1, 3, 2. Let's say different name, label it A, B, C. They are all same set. Order of the element in the set does not matter. A set has no order. Okay? Okay. So this was order of set. Now we're gonna stop here, and in the next lecture we will develop this concept more slowly. We don't have to hurry up. Okay. Thank you for listening.